Hi, I am Murat and I will present Assessment of Energy Saving Potential of a PCM Integrated Sunspace. United Nations Framework Convention on Climate Change adopted the Paris Agreement in December 2015. According to this agreement, the increase of the global average temperature should be kept under 2 centigrade degrees, and if possible, limit that to 1.5 centigrade degrees, since this would significantly reduce the risks and impacts of the climate change. To reach this goal, different solutions are proposed, such as converting current energy plants to renewable energy plants, reducing heat transfer from buildings, fabrics, utilizing environment-friendly sources for energy production, and storing excess heat for later use. Because nearly 40% of the end-user energy is used for the building sector, one of the main challenges against the global warming is reducing energy. To achieve this reduction, new buildings are designed with energy-reducing systems, while the old buildings are retrofitted with new technologies throughout the world. One of these newly applied technologies is sunspaces. They are considered one of the passive solar heating technologies, and they are getting remarkable attention because of their energy conservation potential, multiple usage purposes, attractive and contemporary design. With the correct design of the sunspace, a significant energy reduction can be seen. To increase this energy reduction, sunspaces can be used with energy storage solutions, such as phase change materials. Phase change materials are widely used for latent energy storage. These materials will store a significant amount of energy and release it at a constant temperature. This increases the thermal comfort of the house while also reducing the energy requirements. In general, PCMs are used inside the building structures, such as wall and floors. Because of the different phase change temperatures of the different phase change materials, different sections of the house can be held at different temperatures, which improves the energy efficiency of the building. There are a lot of studies are being made involving sunspaces and PCM implementation. For example, with the implementation of the sunspace, Alicina and his friends showed that with even small investments, the energy requirements for the buildings can be noticeably reduced. Çagri and his friends found that the sunspaces in uninsulated buildings can significantly reduce the energy requirements, but with insulated buildings, a feasibility study should be performed. Feng and his friends found that buildings with sunspaces have required less working time for the heating systems. Aleni and his friends investigated the impact of the zone, orientation, ventilation, shading devices, glazed surface layers, and find the order of importance for these conditions for sunspaces. Vukadinovich and his friends investigated PCM location inside the sunspace wall and found that the most efficient wall configuration is when the PCM is in the middle. Lu and his friends combined sunspace with PCM and found that nearly 55% energy reduction compared to the reference case. In this study, the effect of sunspace integration on a detached house in Istanbul is evaluated. Sunspace depths, glazing types, active shading, and PCM integration is investigated. For sunspace depths, 75 cm, 100 cm, and 125 cm was selected. For all depths, 3 commercial and 3 custom glazing types were selected. For all glazing types, active shading device was turned on and off to investigate the effect of overheating. In addition to that, PCM implementation was investigated by changing the partition wall construction. When we add the reference case, which has no sunspace, a total of 73 analyses. Here we can see the properties of the construction materials for the selected house. As we can see from the table 2, the properties of the PCM is changing based on its state. This means the U value of PCM is variable and depends on the solid-liquid mixture of the PCM. To compare the effect of the sunspace and the addition of the PCM, an annual thermal analysis was conducted, and required heating and cooling loads are found. To compare the overall economic gain, both cooling and heating loads are supplied with a heat pump. The seasonal energy efficiency rating and the seasonal coefficient of performance of the heat pump are taken as 4.4 and 3.8 respectively. A systematic abbreviation is developed to express the features of the sunspace structures for easier understanding. For example, 1.25 SS DGWS corresponds to the 1.25 meter depth sunspace with double glazing incorporating an active shading device. Meanwhile, 1 SS SGWOS corresponds to the 1 meter depth sunspace with single glazing that does not incorporate an active shading device. In this slide, we can see the annual heating requirements for all of the cases. As we can see, with the addition of the PCM to the sunspace, the heating requirements are getting lower. The base case scenario for heating is found with the 1 meter sunspace with custom tree glass without an active shading device. The worst case scenario for heating is found as 3159 kWh with the reference case. It means with the addition of the sunspace and PCM, all of the cases provide better results for heating. In our next slide, we can see the annual cooling requirements for all of the cases. As we can see, with the addition of the PCM, nearly all cases show better results. 1 meter sunspace with custom 2 glass with an active shading and 1.25 meter sunspace with custom 2 glass with active shading shows the worst results. Base case scenario for the cooling is seen with 0.75 meter sunspace with custom 2 glass with active shading device, while the worst case scenario is seen with the 1 meter sunspace with custom 3 glass without an active shading device. As we can see, some of the cases are providing worse results compared to the reference house. Because sunspace always contributes positively to the heating load, but sometimes the effect of the cooling load negatively, an economic analysis must be made to investigate the feasibility. With this graphic, we can see the annual energy cost for heating and cooling for all cases. As we can see, with the addition of the PCM, all of the cases show improvements. With the addition of both sunspace and PCM, energy cost can be reduced up to 16.52%, while the addition of the only sunspace achieves 14.26% of energy savings. Because of the overheating problem, energy cost can be increased by 11.53% for the worst case scenario with the addition of the sunspace. When we implement the same case with PCM, this increase reduces to 0.75%. Addition of the PCM to the sunspace always improves the thermal characteristic of the house. With the addition of the PCM, maximum improvements are observed for 1.25 meter sunspace with custom 3 glass without active shading device by 9.91%, and while the minimum improvements were observed for 1 meter sunspace with custom 2 glass with shading by 2.63%. With the addition of the PCM, required heating energy was always reduced. While the cases 1 meter sunspace with custom 2 glass with shading and 1.25 meter sunspace with custom 2 glass with active shading showed increased cooling energy requirements. Here are some references that I used for this presentation. You can see my full references in my paper. Thank you for your attention. If you have any questions, I can now answer them.